Hello everyone, we're going to do a second problem, and before we do that second problem, I want to define a few other terms that you might see in other places. In the problem that I did in the first video, everything was moving horizontally. You're driving along the road and it's just in some direction. But you could also have vertical motion. And so, you can just imagine taking an object, tossing it in the air, and then it falls back down, or tossing it downwards. And we have a term for such stuff, free fall. So when we have something in free fall, the only force that could act on it is gravity. So the gravity is the only thing causing the motion um, of the object. Right? So what does that mean? Well, it gives us some information about the acceleration in the vertical direction. Right? There's always going to be a downwards pull on the object. Something's going to pull it toward the center of the earth. And for us, that's going to be downwards until we start talking about other motion. And this is always going to be that the acceleration is 9.8 meters per second squared, which this is defined as the vector g. This will come up in other places. This is the gravitational acceleration. And this has, more precise numbers. There's what's called the standard version, which is 9.80665 meters per second squared. And what I'll often do is that, say, A is approximately 10 meters per second squared. If I don't care about the accuracy, I just want to get a rough idea of what's going on. 10 is enough. If you're solving problems for WebAssign, your acceleration is always 9.8. Coincidentally, this is almost pi squared, meters per second squared. But that's just a coincidence. Actually, it's not. It has to do with, oddly enough, clock pendulums and trying to define the meter. And we'll talk about that at the end of the semester. But when we have free fall, we now talk about things moving vertically. Now, this is excluding, all right, if we have a rocket motor attached to the thing, then the rocket motor provides some force. Or if you go, then we're pushing it along and we don't have free fall. Or if we have something that causes a lot of air resistance, a lot of drag, that would prevent free fall. But almost all the time, if we have an object moving through the air, we can usually pretend that it's in free fall. All right, we cannot identify anything but air resistance, and we can ignore it. So we're going to do a problem. I drew a picture to start out with, and it's not much of a picture, but the idea is we're going to throw an object downwards, and we're going to throw it off a cliff. So there's some water here for it to splash in. We'll put some water in. And we know when we threw it, and we time how long it takes to fall, and we figure out that for it to fall 100 meters, it falls 3.5 seconds. And so what we would like to know is, how fast did we throw it, and then how fast did it hit the ground? Now, when we're reading this problem, there's some assumptions here. If we're standing on a cliff, and we're throwing an object, then it's on Earth, which means we have g is 10 meters per second squared. And we have Once we throw it, we're not touching it anymore. As it falls through the air, this is free fall. So this is our acceleration. And one other thing we can know is when the object reaches the ground, it's not going to stop, right? It is not zero for the final velocity because it has to fall, all right? And as it falls, it's going to be speeding up. Our velocity starts out in that direction, and the acceleration is also in this direction. And as y'all are learning from the lab, if V and A are the same direction, it's speeding up. So whatever velocity we start with, it has to get larger and larger and larger and larger and larger. And there's no way it can go from a very large value to zero. What happens is when it contacts the ground, it experiences new acceleration, which will be upwards. And that means it's a new sort of motion. So whenever we talk about a problem like this, if we want to go between different segments of motion, we have to deal with those segments separately. And we don't care about what happens after it touches the water. We only care about its motion at the instant before. So, regardless, we can figure out what V initial is. That's not too bad. The idea is that we organize our information, right? We need to put in some starting point. And so usually what we do is we pick some place that'll be x equals 0, and it doesn't matter where we pick it. So in red, I want to pick x equals 0 here, and usually we set some positive direction with that. Now, what I do almost always is set up as positive. Now, in green, we can pick another spot. We can come over here and we can say that this is x equals 0 and pick up as positive. Right? So if we do that, all right, if we have these differences, what will happen is x initial or x0 or xi is going to be 100 meters up. And so delta x is minus 100 meters. Right? Because we start here and we go down to 0, which is our x final, as well as our origin. And so we get 100 meters. However, in red, if this is our x initial, then x final is minus 100 meters. We went downwards, went in a negative direction. And so delta x is minus 100 meters. And this should make sense to you in a sense that the thing that matters is that it fell down the cliff, or we threw it down the cliff. And it shouldn't matter if we start our measurement at the top, all right, and figure out how far it went, or if we started at the bottom and we figure out how far it traveled, right? Where we put the end of the ruler doesn't matter. I can put it across the room here, right? And that distance is still 1 3/4 inches, no matter where I put the end of the ruler. Still the same distance. It's still 100 meters fall, whether I put my 0 at the ground or at the top or at the center of the earth or somewhere in space. Right? It doesn't matter where I put it. It doesn't matter where the positions are. The displacements, the delta x's, are the same. So we can list our variables. We'll have delta x is minus 100 meters. We don't know v initial. We don't know v final. We do know the acceleration is minus 10 meters per second squared. And we know the time is 3.5 seconds. Okay. So we look at that and we think, well, We need some way of calculating the initial. And if we go back a ways and think about our main equations, these four, right? Really, stick if you can with these two. These two, stick with the equations of motion. These derived ones are useful, but these kind of give you some help. But notice that almost all of these involve a final velocity somewhere. We need one that doesn't since we don't have it. And so if we want to get V initial, what we want to work with is the position equation of motion. Delta x is, I should keep marking these consistently, V initial t plus 1/2 at squared. And then we can solve this. So at any point that you feel comfortable plugging in the numbers, you can do it. But if you work with the letters, you can generally come up with general formulas that are useful, and you see how things manipulate around, and you don't make mistakes like dropping signs, because the signs don't come in until you put the numbers in. So if I rearrange this, what I'm going to do is isolate the initial. So I'm going to subtract 1/2 at squared. And then I'm going to divide the whole thing eventually by t. And so I have delta x minus 1/2 at squared is v naught t. And then I divide both sides by t. And we want to be careful that if we're ever solving an equation where we think one of the solutions might be time is 0, we want to make sure we're not dividing by 0 anywhere. Here, we know it has to fall, and it takes some elapsed time. We're told what it is, so we're okay. So what we'll have is delta x over t minus 1/2 at is v naught. Now, we've isolated this. All we got to do is rearrange it. We can solve. We can take our equation here and move some paper down. I want this to follow one after the other. We can go through and say v is delta x over t minus 1/2 at. And we can plug in. We have 100 meters over 3.5 seconds. And that term's a velocity. It's distance over time, so that's good. And we have minus 1/2 10 meters per second squared times 3.5 seconds. And that is a velocity. That's, acceleration times time. And so we can calculate what those are. We go in and we say 100 divided by 3.5 is, so this first term is 28.6 meters per second minus, and then we'll have 0.5 is 1/2 times 10 times 3.5. And we notice as we do that, we have an epiphany that we've made a mistake somewhere. I'm going to continue on. This is going to be 17.5 meters per second. And what we get is that it slowed down. We end up getting a small velocity. We end up getting something like 28.6 minus 17.5 is 11.1 meters per second. How are we, like I already said, we messed up. I just saw where we made the mistake. And if you see it, you're probably wondering why I'm not fixing it. How would you know if you didn't have the mistake? How would you know if you're making it? Well, you need to make sure that all your calculations are consistent. The idea is that we need to, at some point, go back and check that what we get makes sense. So if we continue this on, we'll get, what we'll get is the initial. So we'll continue it on, and we get that V final, if I work it out ahead of time, is just going to be taking this number plus acceleration times time. And so it'll be plus 35 meters. So V final will be 46.1. And then we check, we plug it into another equation. And if I plug it into the one that doesn't use time, I'll have 46.1 squared minus 11.1 squared. And we're going to divide by 2a. Divide by 2. Divide by a is 10. And it works out. All right, so sometimes you check your math and it works out. But I have made a mistake here. You have to be careful. Sometimes you check, you plug it into another equation. The mistake I made here is that A, the way I've stated, is negative. And that means this term is positive. And so this V initial is 28.6 plus 17.5 is 46.1 meters per second. Or is it? We check the other way around. Does this make sense to us? One thing we can check is if we multiply this to change units from meters per second to miles per hour, it turns out that there's about 2.25 meters per second. Sorry, 2.25 miles per hour per meter per second. So we multiply this by 2.24 or 2.25. It's 103 miles an hour. So if we're not a major league baseball pitcher, and we have to be a pretty good one at that, that doesn't make sense either. Have I made a mistake here? I don't know. We're going to pause for a minute and see where I made a mistake. So, did y'all see the second mistake I made? The distance that the thing falls is minus 100 meters. That's our displacement. There's a minus sign here. There's a minus sign here. And this is wrong as well. So incidentally, we got the right speed. It is 11.1 meters per second, but it's down. It's a negative velocity. So, yeah, you can make contradictory mistakes, and they cancel out. You have to be careful. You have to check. You have to always look and say, am I putting in what I think the right numbers are for everything? All right, anyway, now we can get to V final. We can ask, what speed does it hit the water? And that's easy enough. We use the other equation. All right, we use, from acceleration is change in velocity over change in time, or dv/dt. We'll have v at some time t is v initial plus at. So the velocity when it hits the water is, well, the velocity it starts with, which is what we just found, plus the acceleration is minus 10 meters per second squared times 3.5 seconds. Right? And then now we can calculate that out. This part we know, this part is going to be minus 35 meters per second. And so V final is going to be 46.1 meters per second. And that looked like the wrong answer I got before. Sometimes these equations will get you the right answer by the wrong method. You have to be careful. Not every method you apply makes sense. So you at least want to check that when you get your information, you end up with consistent calculations. And what I'm going to do is I'm going to check this in green, and up here in the corner, I'm going to say, completely as an aside, delta x has to equal 1/2 v final plus v initial times t. I'm going to calculate what this is. So 1/2 minus 46.1 plus minus 11.1 times 3.5 seconds. I'm running out of space, as you can see. 3.5 seconds. And meters per second, so I'll get them meters. And we calculate this out. 46.1 negative plus 11.1 negative divided by 2, 28.6 times 3.5, that is minus 100.1 meters. We've rounded, but we get the right answer. We're good, as far as we can tell. Now, there might be another mistake in here. At some point, we're going to have to trust that everything's consistent. It makes sense. We're not throwing the rock 100 miles an hour. We're throwing it 25 miles an hour. And that makes sense. All right. You can check if we threw an object, at 46 meters a second, you can check that it should take at least, it should take no more than 100 divided by 46 seconds. It should take no more than about 2 seconds, but it takes 3. So we know that something was off there. And we go and we check and we find all our errors, and we're confident everything's consistent. This is what you have to do to solve a problem. These things are not horribly difficult problems, but it pays to sit down and organize your information. You have a table where you're sorting stuff out and you're writing it down and you reference it. You go and you make sure you've actually plugged in the stuff that you've written down. And you draw a picture, and in that picture you lay out, which direction's positive, where your zero is. And you can do things like lay out what is the acceleration, what is the velocity, and make sure it makes sense. And then you should also, like, I'm not an artist, but you should put in some art, right? We put in some water, and you can put in a fish here, maybe a couple of fishes and some birds. And if you want, you can put a nice tree standing here behind you. I should do it in green, but I don't have that marker. So there's your tree. You do some stuff to where it distracts you for a few seconds and gives you some imagination, some creativity to go through. It's not just, we don't want to just calculate everything. We're talking about real world problems. Maybe they're simplistic, but that's what we're going for. We're talking about organizing our brain as well as our information. And part of that is addressing the part of the brain that's bored because we're doing calculations. So, I hope this helps. We're going to do more problems. If this doesn't make sense necessarily, then just follow it for the basic information I wanted you to have. Free fall and the organization of problems. So that said, that's another 25 minutes. I'm going to stop there, and we will start again with a third problem.